Hello, welcome to the video on partial fractions. This will be a lesson on this topic, and this is going to be part one of this lesson. Of course, there'll be a separate video for part two. This is a pretty big topic. A lot of things kind of going on. Once you master it like anything else, you'll be able to kind of understand it completely, and you'll say, okay, I understand the different pieces. But when students typically first learn this, it can be a little bit overwhelming. So my suggestion, if this is the first time, if you're watching this video, just watch the video and then maybe, again, watch it again and take notes, and you'll probably need to reference it a couple more times. Of course, when you practice this in the example sets, that's going to really strengthen your skills. So this is the first part of our objective, and then there'll be a part two, which will basically finish the process. So just sit back, relax, and let's kind of enjoy the video together. And let's get right to our objectives. So the objectives for this video, this lesson, is one, we're going to go and explain what partial fractions are and understand why they're important. Okay. Then we're going to learn the patterns of decomposition. Don't worry about this language. I'll explain all of it. Okay. Then we're going to understand how to write a partial decomposition form of a proper rational function. Again, I know this probably means nothing to you right now, but just hold on, it will make sense. And then lastly, we're going to actually find a partial fraction decomposition of a rational function. But we're going to do that in part two of the lesson, but this will complete the skills for this particular topic once we cover what we need to cover in part two. All right, so let's get to it. What's this all about? Okay, so partial fractions. What's the big deal here? Okay, so let's just ignore this over here. Okay, this rational expression. So let's say I told you, and I gave you a little question. I said, add these fractions up. Okay, so you being an astute student would know how to add rational expressions. You'd add them all up, and this would be your answer. Okay, no big deal. Now let's reverse the kind of the question here, if you will. Let's say I said, here is a rational expression. Can you write a set of simpler fractions such that when you add them up, you get back to this? Now that is much more challenging, but it's absolutely critically important that we learn how to do that, okay? So the idea with partial fractions is we want to take a rational expression and we want to break it up into the sum of simpler fractions. If I add up these guys, I get back to this guy. Now, why would I want to do this? Why is this so important? Well, in more advanced math like calculus, oftentimes we do things, there's multiple different things that you do, but one of the main things that you do in calculus, or a big thing you do, is find the integral. This again probably doesn't mean anything to you, but integration is kind of like adding up the area underneath this function's curve. It doesn't make a difference. Well, you obviously don't understand this probably at this level, but just trust me when I tell you, integration is absolutely critical to calculus, advanced mathematics, engineering, science, you name it, okay? So in order to do this problem, to integrate this particular problem, it can be quite difficult to actually do this problem. However, if we could break up this rational expression into its parts, okay, to the sum of simpler rational expressions, I can integrate individually each one of these little guys here. Okay, and to do this, the answer is much easier. It's much quicker, much more effective. So the main reason we're learning partial fractions is to be able to decompose, break down into its parts, a particular rational expression into a sum of smaller ones. So therefore, we can do things like integrate across them. Okay, so that's why we're doing this. Very, very, very important. You're guaranteed you'll be using this. Obviously, whatever course level you're doing now, this is typically at the pre-calculus level. But if you're heading into calculus, you'll see this again and again and again. Okay. Now, a few things here. The first is we're going to be focusing on proper rational functions, okay? That's what we're going to be doing partial fractions with, a proper rational function. Just like a proper fraction, okay, like say 2/3, this is a proper fraction, okay, because the denominator is bigger than the numerator, okay? This is an improper fraction because the numerator is bigger than the denominator. Same thing here. When the degree of the numerator of the rational function is less than the degree of the denominator, okay, then you have a proper rational function. For example, this one here is a proper rational function. This is second degree, this is third degree. And by the way, we're talking about polynomials, okay? So just to review, the definition of a rational function is a fraction consisting of a polynomial in the numerator and denominator, okay? So partial fractions are restricted to really what we're going to be doing to proper rational functions. Now, you can do things with improper rational functions and use what we're going to be learning in those type of problems, and you'll see this probably in some of the example sets. But an improper rational function, let's say I have this scenario, okay, just kind of reversed it. Now the numerator has a higher degree than the denominator. What I can do here, if I wanted to break this up into simpler fractions, I can do polynomial long division. So you may hopefully remember what this is. This goes along with synthetic division. Remember, we're trying to find the zeros of polynomials. But I can divide this into this, and I'll end up getting an answer plus a remainder. Okay, so basically I'm going to end up with two smaller parts. So when you have an improper rational function, you could perform long division, which is going to definitely help you out. But anyways, the majority of our focus is going to be on these proper rational functions with partial fractions. Okay? All right, so the main idea here before we go forward is we want to take a proper rational function and we want to break it up into parts, the sum of smaller fractions, such that when you add all these guys up, you get back to this, okay? And the process that we're going to be using for this is called partial fraction decomposition, okay? So we're going to use a process called partial fraction decomposition. And now what I'm going to show you for the next few minutes here is going to be somewhat rather complex, but I want to show it to you because it's important. When you're studying mathematics, you need to be able to see the formal definitions, and you need to be able to read them and get good at reading them. It's just a sign of maturity and this kind of level of mathematics. So I can explain this to you in a much more basic way, and you go, oh, okay, I kind of get that, but that's not going to help you strengthen your interpretation of formal mathematical definitions, etc. Okay? So with that being said, let's go ahead and take a look at the patterns of decomposition. So I'm just going to scroll down here real quick to show you what I'm going to read. Okay. So just imagine you had to read this. You might be like, I have no idea what this is saying. Maybe you're like, oh, I totally get this. But this is mathematics for you, okay, at a higher level. So you have to be able to read things like this and decipher them. So that's why knowing these terms, languages, and the vocabulary of math is so critically important. So I'm going to read this to you, then we're going to read some other stuff. Then this is going to make sense later. So hold off on taking notes. That's my suggestion. And then, I think you should watch this video again, then take your formal notes. That's, like I said, that's my strong suggestion to you, but you do it the way you want to do it. All right, let's get to it. So given the proper rational function, we just talked about what that is, f of x equals p of x over q of x, okay? Assume q of x, that's the denominator, has been completely factored as a product of factors of the form, okay, it's going to be in one or two forms, ax plus b to the n power, and or ax squared plus bx plus c, all that to the n power, where a, b, and c are real numbers. Okay, we all know what real numbers are, not complex numbers. Ax squared plus bx plus c is not factorable. Sometimes they use the word irreducible. Okay, so you might say it's not irreducible, but that just means it can't be factored anymore. Over the real numbers in m and n, Okay, the exponents here are positive integers. Okay, this is kind of like setting up the conditions for what decomposition is. Then the function f of x can be decomposed as the sum of simpler rational functions where 1, each factor of the form ax plus b to the m leads to the sum of the form of the following. Okay. Then 2, each factor of the form ax squared plus bx plus c to the n power leads to the sum of the form of this following. Okay. It's important that after we go through this that you're able to read these formal definitions and understand it, because this is what's going to be coming at you as you progress in math. Okay. So it probably doesn't, and I don't blame you if you're like, I have no idea what this means. Hold on, you definitely will. Okay, so let's get to what we're talking about. Okay, remember just keep in mind the main thing we're trying to do is learn the process that takes a proper rational function and get to this point. Basically we're going to find smaller fractions that add up to this larger one. That's the whole object. Okay, but what we're going to be doing though first is we're going to be learning kind of phase 1, part 1 of this process, and then in the second video we'll talk about phase 2 to actually find it. So obviously there's a good amount of work we have to do in order to solve these problems. Okay, let's move on. So how to write a partial decomposition form of a proper rational function. Okay, so here's the steps you're going to be taking. Okay, 1, we're going to factor the denominators. This you should just kind of stick into your brain here, right? So we want to focus on factoring the denominator. The denominator of what? The denominator of the proper rational function. Okay, so whatever the proper rational function is, that denominator, our main first task is to factor it. Okay, and sometimes it's not so easy to factor it, right? But you need to use all methods, including synthetic division. So remember synthetic division when you're trying to solve a polynomial, when you're trying to find the zeros. If you find a 0, those are also, you can write them as linear factors. So go back and review that as well. You probably maybe need to do a little brushing up on it. But synthetic division can be a part of the tool you use to find the factors of the denominator. We need to be able to factor the denominator to write partial fractions. Okay, so that's the big first step. Okay, number 2, or step 2, we're going to write new fractions in the following form. So these are kind of general guidelines, and you'll see some specifics here. So each factor, okay, once we factor the denominator, each one of those factors will have its own fraction when we write this new form. Okay, factors that are powers will have individual fractions containing increasing powers of the factors. Again, hold on, you'll see what I mean by that. Okay, but I just want you to get your mind kind of conditioned to what I'm talking about. And then the numerators of the fractions are expressed as variables. All right, so there's 2 basic factors that we're going to be looking at. Okay, so this right here, again, I want you to get used to seeing, right? The first is linear factors and the second is quadratic factors. So this is a linear factor right here, ax plus b to the m power. So when we have factors of this, we're going to be using this pattern. Okay, and then when we have quadratic factors, we're going to be using this pattern. Okay, now a bunch of variables and all that kind of stuff like that, don't let this scare you. It's not as difficult as you think. Again, I want you to make the connection, I want you to understand this, to the language, because I can tell you right now, having a degree in theoretical mathematics and doing a lot of stuff, sometimes you get into courses, advanced courses, and the instructor, professors, they're going to be like, you got to be able to decipher the book. Okay, you got to be able to decipher the formal definitions. So you want to start training yourself to be able to read this kind of formal language. Again, I know I'm repeating myself, but it's important that you just don't skimp over this. Okay, you need to know these formal definitions. Okay, again, hold off on taking notes. Let's move forward. All right, so we're talking about linear factors and quadratic factors. Let's make sure we understand what those are, okay? So a linear factor, if we factor the denominator and we end up with factors like this, the denominator of the rational function, and we end up with factors like so, these are linear factors, okay? In the form of ax, a number plus in front of an x plus another number. Okay, you follow that? That's the ax plus b. Remember, a and b are real numbers. So these are linear factors. Now, just because this has a power, that's okay. That's the m part here, okay? Linear factor, linear factor, linear factor. You need to recognize that, oh, these are linear factors because you're going to be using a particular type of pattern for those guys, okay? Now, x cubed down here, you might say, well, that's a linear factor. Yes, that is, because I want you to think of it like so. X to the first, right? If you want to get very technical, let's take a look at x cubed. X cubed, you can think of it in the form of ax plus b to the m, right? So I could write that as 1 to the x plus 0, okay? And that'd be to the third power, right? So this is going to be plus 0, and then basically you'll get your cubic there, okay? Just so you know, this right here is considered a linear factor, all right? Now, over here we have quadratic, okay? Now quadratic, you need to be able to recognize that. These trinomials like so, or this trinomial here is like a quadratic function. So if you see this as a factor, and by the way, the factor has to be non-reducible. In other words, you cannot factor this trinomial down. So if you factor this trinomial and end up with two linear factors, then you're going to use the linear pattern. Okay, if you factor completely and you can't factor anymore, then we're going to have the quadratic pattern. Okay, this is a quadratic factor because we have an x squared inside of it. Okay, don't confuse that with the x cubed. That's by itself. Over here, this is a factor, x squared plus 5 with parentheses around it is a factor in and of itself. You can't factor this anymore, all right? So this is quadratic, right? X squared plus 7 to the third power is a quadratic factor. Again, you have the x squared being added to another number, all right? Then now that to a power. So this is a factor that cannot be factored any further, all right? And then down here, again, you have another example of a quadratic factor. All right, so quadratic factor, linear factors. So hopefully you can understand the difference between the two. Again, when you see the quadratic factors, you're going to be using a different pattern than the linear factors. Okay. Now, note when we write each fraction is going to have a different variable assigned. So when we use this ax plus 1, when you write a letter down like a or b, you're never going to write it again. Okay, you're going to use a, b, c. You're going to keep going to new variables. Just kind of keep that in mind as a rule of thumb. You're not going to write a again, like a once and then a again. You can use a1, a2, like this over here. You might be a little bit confused. Let me scroll up here. Like these, a1, a2, b2. Just get used to using large cap letters, and you're only going to write them once. So the patterns kind of look like this, all right? For the linear factors, now imagine we have our factors of the denominator. So what we're going to do is, for linear factors, we're going to put large A, okay, an uppercase A, and we're going to write a fraction over the first factor, plus B, and we're going to write that over the second factor that we have, the factors that make up the denominator. And then we're going to continue the pattern, okay? For the quadratic, we're going to have, we're going to write ax plus b. This is a small b, you can put a big B, okay, either way, over the first factor, okay, plus the first, and by the way too, this is the quadratic factor here, okay, plus cx plus d over the second quadratic factor, and so forth. Now, very, very critical thing that we need to learn is what happens when we have powers like x cubed. This is a linear factor to the third power, or this quadratic power, or this quadratic factor to the second power. So when we have these linear factors or quadratic factors to a particular power, okay, then we have to do some additional work. It's not hard, but we have to keep this in mind. So factors that are powers will have a fraction for each increasing power. Just make sure you kind of like pay attention to this when I go over it. Okay, so when we have powers, whether it's a linear or quadratic factor to a power, then we're going to have to represent each power of while how it's increasing with the fractions. Probably harder than say to actually show it. So at this point, you're probably thoroughly confused, and maybe I'm overstating it. Hopefully you understand. But when you see some real examples, you'll be like, oh wow, this is so much easier than it sounds, and yeah, I think that's actually kind of true. Okay, so let's get to it. So we want to write a partial decomposition form for the following proper rational functions. So this is our examples. Okay, so let's take our first function. So here I don't have a numerator. Okay, I just want to kind of set up the form to get this kind of do the first step in finding the answer. So the first thing we want to do is you want to factor the denominator, right? We talked about that. So we want to factor it completely. Okay, now down over here, you can see that I have these factors. X squared minus 6, that's quadratic. You don't go to the quadratic form. You try to factor it completely. Remember, until it's irreducible. So this does factor, and I end up with two linear factors, all right? So because I have linear factors, I need to use the linear pattern, okay, of decomposition, and it looks like this in its formal form, but all that really means to us is following. Okay, 1, we have no powers here other than 1. There's no square, no cubes, so it's very simple, okay? So I'm going to put an A over, I'm going to use the first factor, right, x minus 3. Then I'm going to put plus, then I'm going to use another variable, b, okay, over the second factor, and I'm done. That's it. They're like, wow, that's it? Yes, that's it. So this right here, I mean, obviously this is a beginning problem. It's like our goal for phase 1 to solve these problems. Now, what we want to do, obviously, is we're going to work on finding the numerators so we can actually determine the actual simpler fractions. That's another video, okay? But we need to first be able to set up the decomposition form correctly. All right, so that was the easy one. Let's kind of kick it up a little bit. All right, so here is a function here. So let's write the decomposition form for this guy. All right, so let's study the denominator. Okay, so we have these factors down here. So you have to ask yourself, can these be factored anymore? No, we cannot factor them. Okay, so you don't want to be using square roots and nothing like that. X squared plus 2, x squared plus 5, they're pretty much factored out. Now, if we notice, these are quadratic factors. These are not linear factors. We have the x squared inside the factor, right? So these are quadratic factors, so we're going to use the quadratic form, right? And you can see here, this is what we told you what it was, or what I told you what it was. But let's see how we write that. So we're going to write the first factor, x squared plus 2, over ax plus b. I said you can use lowercase b or c. Let's stay consistent. Let's use the uppercase. So ax plus b plus the second factor over, we're not going to repeat any of these variables, cx plus d. And then we would just keep going. If we had another factor down here, we would write it, okay, plus what? A, B, C, D, E, X plus F, and so forth. All right? So if you're like getting this, then this is the object, this you know, that kind of the end goal. So much easier. You're like, wow, that's a lot of explanation. But there's some technical things in there that you really need to know. So don't minimize at all, okay, everything I told you. You need to go back, watch a video again, but it'd be easier when you watch a video a second time and take notes. You'll be able to really kind of understand better what things are saying. Okay, let's take a look at our last example. And of course, you need to do the examples. That's because they're going to be, you know, a variety of different type of problems. So here we got a function, and we have let's take a look at our denominator, right? So denominator, this is a linear factor here, right? It's linear, okay? But it's squared. We have a squared going on. So this is the first time we're going to be doing something with the squared, or a power, a factor to a particular power. And then this is a quadratic to a power. So we have both linear and quadratic and powers going on in the denominator, the factors. And we look here, and this is completely factored as well. So mission number one, where we're dealing with this, you got to completely factor the denominator, and then we got to determine, okay, what do we got? We got linear factors, quadratic factors, powers of factors. You can have everything all together in your denominator, right? There's no rule that's only one or the other, okay? So this is what we need to do. Let's go ahead and address the linear factor first, right? X plus 5. So the way you do this, okay, is the following. So we're going to write a over x plus 5. Now you're saying, well, why not we write x plus 5 squared? Well, you have to write for a fraction, an individual fraction for each increasing power. So this is 1. Okay, we don't write the 1, but technically there's a 1. So we got a fraction here. So plus b, remember this is the pattern for the linear factor, over x plus 5 squared. Now if this was x plus 5 to the third power, I would write plus c over x plus 5 cubed. Okay, so that's what we mean by writing a fraction for each increasing power. All right, so we got to write one for the first power, we got to write one for the second power, and so forth. But we have to use a linear pattern because this is a linear factor. But we're not done. Here we got to address the quadratic, right? X squared plus 3, that's quadratic, and it does have a power. So we're going to use the same rule, okay, same concepts, but now we have to use the quadratic pattern. Now notice I used the A here, a B here. Now I can't use these letters again, so I got to continue on with the C over here. So this is going to be cx plus d over x squared plus 3 to the first, right? We don't need to write it to the first, but that's what it is because I have this to the second. And then so I got to write another fraction so I can get that second power in. So that's going to be, I can't use the same letters, A, B, C, D, E, F, G, right? So ex plus f, okay, over x squared plus 3 to the second power. So this is our linear power, this is our quadratic power. So this would be the decomposition form of this right here for this particular problem, okay? So it's a considerable amount. You can clearly see that, well, you know, there's rules and things that we have to follow. So, you know, if you're like a little bit lost, definitely watch your video again, and you got to practice. Do not move on to the second part 2, second half of this video, the part 2, until you master all this, because this is a lot just in and of itself, okay? All right, so let's go and wrap this up. And in review, all right, being able to write proper rational functions as a sum of simpler fractions is very helpful in advanced math like calculus. Okay, I can't stress that enough. When you get to calculus, you'll be doing this. And so another helpful tip is the notes that you're taking with me here, you should keep. Okay, you should keep. Your notebook should be like pristine, at least as nice as you can make it, because you can reference it always in the future. And sometimes, oftentimes in these calculus classes, you're gonna be like, oh yeah, you already took that course, or you already know that material. So, you know, you're kind of expected to know these things. That's why it's important to keep your notes. All right, the second thing is to write a rational function as a sum of these simpler fractions, we use partial fractions. The first step in the process is called decomposition. And that's what, you know, we were really focused on with these examples. So to determine the decomposition pattern, you must fully factor. That's, you know, key. Fully factor the denominator. So you got to do everything you possibly can. Maybe synthetic division included for, you know, like third degree, fourth degree, etc. So fully factor the denominator of the rational function denominator. Then you're going to have linear and quadratic factors, and each of those guys are going to have their own individual patterns, as we have seen. And then lastly, factors that are powers will need to have separate fraction for each increasing power. Okay, so that's kind of going to be a wrap for this video. Hopefully I did a pretty good job of explaining everything, but let's go back and look up here. All right, mean, I distilled this down. Oftentimes, a textbook will give you just the following to explain everything that I just did. So you should challenge yourself to say, hey, can I read this and kind of pull it all together? Can I understand what he's saying? If you can do that, that's really good. You should really strive to be able to, read these formal definitions and kind of connect the dots. Okay, it's part of, kind of condition your brain for a more and more advanced math. Not only advanced mathematics, but just more advanced, complex, critical thinking skills. But anyways, got to do those examples. Look forward to seeing you over there. And thanks for watching the video. Have a great day.